So we're looking at the 2012 AP exam free response question number 4. And this one I think is a fantastic question. Not because it's overly difficult or challenging, but because it hits up a number of different topics throughout. So if you've read the problem, you'll notice that we're given a table and we're given values of x and we're given the values of f prime of x at those specific x values. And if you read through these specific parts, there are actually 4 different things, but they're all asking you to do the same thing. If you look at each different part, in part A, we're trying to approximate f of 1.4. In part B, we're estimating the value of f of 1.4. Part C, you probably know what's coming up. You guessed it. In all of these, we're trying to approximate f of 1.4. That's a common theme throughout, but we're getting there in a number of different ways. So they're 4 separate kind of topics, but I think they're really relevant to what we need to be preparing for this exam. So let's get through a few of these, or all of these, I should say. So in part A, they start off with a little bit of a softball. They want us to simply find the equation of the tangent line at x is equal to 1. So here we're just going to start out with point slope form. So given what we know, y minus, and we know our y value, we're leveraging this bit of information over here, f of 1 is equal to 15. So we know our y value is 15 when x is equal to 1. When x is equal to 1. And to complete the point slope form, we need our slope, and we can look here. We'll see that when x is equal to 1, f prime of x at 1 is equal to 8. So we're going to go ahead and put that in here. So we've got our tangent line equation just in point slope form. And again, don't try to sit there and write this in slope intercept form. You're going to make things more difficult for yourself, and you're going to increase the chances that you make an arithmetic error. Now from here, we're going to use this tangent line equation to approximate 1.4, and this is local linearization. Go back to your semester 1 notes and review that, but this is local linearization. And so from here, we're just going to plug in 1.4 into our equations and see what we get. So let's go ahead and write y is equal to, and I'm going to move that 15 over to the other side, 8 times 1.4 minus 1 plus 15. And with a little bit of calculation, we say 8 times 0.4 plus 15. Well, that's just 3.2 plus 15, so this should just give us 18.2. So we can say f of 1.4 is approximately equal to 18.2. And again, the idea of local linearization, and this isn't the actual graph, but just kind of visualize what's going on here, is if we're given the function of x or f, and we know its tangent line at a specific point, so we're drawing a tangent line, something like this. What we're seeing here is, okay, if this is our tangent line at x is equal to 1, at 1.4, we're getting some value, we're approximating some value 1.4, and we're doing that so that we can try to approximate the actual value at 1.4. So we're approximating f of 1.4 using its tangent line. So this is just a visualization of what we're trying to do here. All right, so for part B, now we're using midpoint Riemann sums, and we're told that we're going to be using 2 subintervals. So let's clear out some of this stuff here just so we don't get too bogged down. So we're trying to use a midpoint Riemann sum with 2 subintervals of equal length. So let's start with the Riemann sum part. So in part B, and while I'm at it, let's just bring that table down so that I don't have to keep scrolling back up and down. So if this is our table of values here, and let's just switch colors real quick. So we're going to come up with 2 subintervals. So from 1 to 1.2, that's one subinterval. And then from 1.2 to 1.4, there's our second subinterval. Specifically, we're using a midpoint Riemann sum. So the midpoint would be here of that first subinterval, and our second midpoint would be right over there. So with that, we can just go ahead and say, all right, the integral from 1 to 1.4 of f prime of x dx would be, let's just finish it off, would be equal to our width, which is 0.2, right? That's our width, that's this region right over here, times our height of our midpoint, which would be 10. And you can just go ahead and add the other midpoint within here if you want, but just so that we can really see the two separate subintervals, I'm going to write 0.2 times the height of the second midpoint, which is going to be 13. And let's see, that would give us 2 plus 2.6, so that's going to be equal to 4.6. Okay, now this gives us the integral from 1 to 1.4. And now we're going to use the fundamental theorem of calculus, specifically the start plus accumulation. So the start plus accumulation method to pretty much say that, all right, f of 1.4 is going to be equal to f of 1, whatever f of 1 is, plus pretty much everything that we just found here. So let's just go ahead and copy that. And I don't need this. And we know f of 1. If we look back in the problem, we were told that f of 1, where is that? Oh, there it is. We know that f of 1 is equal to 15. So this is going to be equal to 15. And we just found the integral from 1 to 1.4. So that's 4.6. And I should be clear here. This is approximately, so we're saying f of 1.4 is approximately equal to 19.6 using both the midpoint Riemann sum and the and the fundamental theorem of calculus. All right. Now let's move on to part C. And part C is a personal favorite of mine. I know it wasn't everyone's favorite, but it's a personal favorite of mine. We're using oh my goodness, I almost said Euler. That would have been embarrassing. I'm almost tempted to stop this recording and try it again. We're using Euler's method starting at x is equal to 1. All right, so I went ahead and then I set up the table already for you guys because I'm considerate. So just to remind you how Euler's method works, okay, we're leveraging information about the derivative to give us a sense of where the actual function f is going. So starting at x is equal to 1, so let's fill that in. So when x is equal to 1, and we've got two steps of equal size, we'll get to that. Our y value when x is equal to 1 is 15. Again, when we have f of 1 is equal to 15. Right? When x is equal to 1, y is equal to 15. What is the derivative, or dy dx, I should say, at x is equal to 1? Well, we see here that it's equal to 8. So what is delta y going to be, or a change in y going to be? Our change in y is going to be dy dx, which is 8, times delta x, or the change in x. So if we're again going from 1 to 1.4, and we have just two steps of equal size, this means that our delta x must be equal to 0.2, right? It's the same idea that we saw in the previous part. So we have 0.2, and so from this, we know that our change in y is going to be 1.6. So going on, using delta x to write our next x value, we've got 1.2 then. So at 1.2, what was our y value? Well, we determine our new y value at 1.2 using delta y. So 15 plus 1.6 gives us 16.6. Now, what is dy dx when x is equal to 1.2? We're not given the differential equation here. We're just going to look at our table again. So at x is equal to 1.2, right, dy dx is equal to 12. So again, delta y is going to be 12 times the same delta x, 0.2, and this gives us 2.4. And then finally, when x is equal to 1.4, y, our new y value, is going to be our previous y value plus now the change in y, or delta y. So 16.6 plus 2.4 is 19. And we can stop because we're doing all of this just so that we can try to approximate f of 1.4. So we can say that at 1.4, we should get approximately 19. So f of 1.4 is approximately 19. Okay? And take a moment and just kind of keep track of your approximations so far. Using local linearization, we saw that our approximation was approximately 18.2. Using the fundamental theorem of calculus and Riemann sums, we saw that was approximately 19.6. Using Euler's method, we're saying that it's approximately 19. We're approximating f of 1.4. And our final way of approximating this would be to use a Taylor polynomial. So, good review for Taylor polynomials. Fortunately, it isn't too bad. We can say that our second degree Taylor polynomial, not a series, but our second degree Taylor polynomial would be the following. It would be f of 1 plus f prime of 1 times x minus 1 to the first power, all of this over 1 factorial, plus now the second derivative, and you probably figured out this is the whole reason why we're given the second derivative. That throughout all of these parts, not once did we ever have to actually look at the second derivative until now. So we're going to stop there. So we've got everything set up, and now from here, all we need to do is just plug in what we know. So f of 1, we know that is 15. That was given to us. Plus our derivative, or f prime of 1, using our table, we know that's 8. Our second derivative, just look back and see what was given there. I believe it was 20. And might as well clean that up now. 2 goes into 20 10 times. So there's our second degree Taylor polynomial. Now our last step is to use that Taylor polynomial to approximate what f of 1.4 might be. So from there, 15 plus 8 times 1.4 minus 1 plus 10 times 1.4 minus 1 squared. It's approximately 15, 8, 0.4 plus 10 times 0.4 squared. And just doing some crunching some numbers, that's 3.2. All of that should give us approximately 19.8. So might as well just bring that down. And there's our final approximation of what f of 1.4 is. So go ahead and review all the parts, but again, I thought it was a great question because it manages to hit up a number of different ways of approximating a function by leveraging information of what we know about the derivative. And it gives somewhat of a connective strand or tissue to some of these concepts that throughout the year may have seemed completely different, but we see the utility of each of those methods, which is to try to leverage information about the derivative to give us information about the function itself.